All right, so integration by parts. Finally, an easy chapter. Now this won't be super easy necessarily. It probably looks a little bit weird to you, but the first time you see it. But it really is plug and chug. There's just a couple of exceptional problems that are sort of tricky to set up. But pretty much on these things, it's always plug and chug, and then you just want to spot certain patterns to help you through them. So, but once you pick your U and your DV, pretty much, that's just the only part of organizing the problem at first. Once you've done that, it's plug and chug every time. So in this video and the next couple of videos, what I'm going to really emphasize is picking the right thing for U and DV at first, which will make the problem just plug and chug. If you don't do it right at first, don't spot which type of problem it is, then that's where you can get into a little bit of trouble on this puppy, get in infinite loops and stuff like that. All right, so one way of looking at integration by parts, it's just a formula. I can't really describe where it comes from, but you can kind of think of it as the product rule for integration. Because the really tough thing about these problems is spotting them. And that's kind of what happens in this section of calculus, is where you've already learned how to integrate stuff like polynomials and sines and cosines and things. And you've learned how to use integrals to do cool stuff like find volumes and areas. But then in this part of calculus, they generally teach you, depending on how in-depth your course is, they'll teach you 1 or 2 or 5 or 10 sort of very specific types of integrals that you could not do with any of your standard U sub or anything, like U substitution and other formulas you've already learned. So they teach you a bunch of sort of trickery to integrate stuff that couldn't really be integrated because the things don't match up. So integration by parts is just the first one of those usually. And basically it's kind of like the product rule for integration. So if you're looking at this first problem here, and you're thinking, hey, I know how to integrate e to the x, and I know how to integrate x. I do not know how to integrate x times e to the x though, because if my u, if you're integrating an exponential normally, this would be your u, which means your du would just be dx, or like 1 dx. This x is not necessary for u sub, and therefore you're kind of hosed on this problem if you wanted to use u sub. Same thing happens here. Sine of x, you know how to find the integral. X squared, you know how to find the integral. But if the two things are multiplied together, now you're hosed. Because if this isn't part of your du, you just can't integrate this puppy with u substitution. So what we're going to do is use the integration by parts formula. So this looks like Greek the first time you see it, but the main point is that we've got a u and we've got a dv. So basically whatever problem you start with, like x e to the x, you're going to need to break that up into your u and your dv. So that's why when we work these problems, we're going to set up 4 little equal signs, picking our u and our dv, and for our du and our v. But once you pick your u and your dv, it's just plug and chug. You got your uv minus integral of v du. So most of the problems in this particular video are going to be of the type with the x squared in front. So you'll notice that this right here, it starts with a polynomial. It's a polynomial times something. And that's kind of always going to happen with integration by parts, is that, or at least for these more basic problems, usually at least one piece of the problem is something that sort of like is its own derivative. For example, e to the x, the derivative of e to the x is e to the x. Second derivative is e to the x. The integral is e to the x. E to the x just doesn't change no matter how many times you take the derivative. So when we're sitting here trying to pick between u and dv, we're going to make our u the x term. So whenever you have an x or x squared or x to the cubed times some, they call them transcendental functions, but things that aren't polynomials, you usually make your dv the thing that doesn't change, so that'd be e to the x dx, and you make your u x. The reason you'll see in a second. So at this point, once you pick your u and your dv, all you do is just, we're going to need du in the formula, so that's why we got to take the derivative of u. So let's get dx for this one. And we also need v, but we just picked what dv is, because the original problem has dv in it. So to get v, you're going to have to integrate dv. So if you integrate e to the x dx, you just get that v, integral of dv is just v, and on the right side, you just get e to the x. All right, so now we've got the 4 things that appear in the formula, so we can just plug and chug through it. First we got our u, which is x. Then we need our v, which we just found as e to the x. You'll notice it's not a coincidence that this and the original problem are pretty similar. That happens a lot. Then we got our minus sign. Never forget the minus sign. That's the easiest way to mess up these problems. Then we got an integral of v, which is e to the x, times du, which is dx. All right, so we're not done yet. It's kind of wacky. We did an integral and ended up with another integral. But the nice thing is that this one's actually integratable. So in the original, we had x times e to the x, and that x really messed us up. But you'll notice that now when we do an integral, it's just the integral of e to the x, which is super easy. It's just e to the x. So there's just x e to the x, and then integral of e to the x is e to the x. Oops. I just did the one thing that you must never do on these, which is mess up that minus sign. I tell you, that's like 90% of the errors on this thing come from that stupid minus sign. And of course, you don't want to forget your plus c either. Probably should have written that right here. Hopefully we'll remember it for all the rest of the problems. All right, so this might not make a ton of sense. You'll see the pattern in a second, though, because what we're about to do is do the exact same problem, only with x squared in front. So let's set this one up. Once again, just like last time, I want to make my u the x squared, the x cubed, or whatever, the x term. So my u is going to equal x squared, and my dv, which is just the rest of the problem. If I use my x squared for u, that means everything else has to be my dv. So that's going to be e to the x dx. All right, so derivative of x squared is 2x dx, and the integral of v is just e to the x. All right, so now I got my fourth thing, so I can plug and chug. So I got uv, so that's x squared times e to the x minus the integral of v, e to the x, times du, 2x. All right, so what happened here? I'm just going to move this 2 out front to make it a little bit more obvious what's going on. So what happened is we started trying to integrate x squared e to the x. And we're like, you know what, the u sub doesn't work for that because the du doesn't match the u. So let's try integration by parts. So we just plugged and chugged through one round. We did integration by parts once, okay? And at this point, we've got x squared e to the x minus 2 times the integral of x e to the x. Now the last problem we did, this integral is really easy to do. But in this one, we still can't integrate. So this term right here, we've got negative 2 times the integral. I'll just rewrite it above so it's less messy. So here's the integral we need to do now to finish up our integral by parts. But the problem is that x e to the x is not something I can integrate normally either. I need integration by parts just to do an integral that came from doing integration by parts. But check it out. We're a little bit closer to being done than we were. Because when we started, we had x squared times e to the x. So we had 2 x's basically, x times x, or x squared to worry about. That was extraneous. Now we've just got an x to the first power left over. And isn't this the problem we just did on the previous slide anyway? Just x times e to the x. So I bet you that if we do integration by parts again on this little integral right here, we'll probably come out okay. Of course, that doesn't mean that this still exists. I mean, we got that. That's part of our answer. We're currently at the step where we got x squared e to the x minus 2 times this junk. So as we work integration by parts again, we're just going to have to be careful to remember to keep the stuff that we just came up with. So as I go down here and I'm just going to recopy that x squared e to the x so I don't forget it. And then we got a minus 2. And now in parentheses, I'm going to put the integral of x times e to the x. So just looking at this integral right here, I've got to do integration by parts again. So I'm once again going to do u equals x, dv equals the rest of it, which is e to the x dx. Du equals dx. Integral, the derivative of x is just dx. And then the integral of dv would give me v, and that's going to equal e to the x. So at this point, in these parentheses, I'm going to replace this integral with the integration by parts with all this junk in it. So u is x times v, which is e to the x, minus the integral of dv, of v, which is e to the x, times du, which is dx. All right, so we've still got an integral to do. Isn't this crazy? But we're getting pretty close now because this is integratable. That's like not too bad at once. So I'll just copy everything down. X squared e to the x minus 2 times x e to the x minus, and what's the integral of e to the x? E to the x. And of course, don't forget your plus c. So what happened here? We had to do integration by parts twice because of this x squared. Each time you do integration by parts, if it's one of these ones where you have an x squared or x cubed or something that you're making your u term, each time you do integration by parts, you knock down that power by 1. So if you have just an x times e to the x, you have to do integration by parts once. you have x squared times e to the x, you have to do integration by parts twice. If you have x cubed, you're going to have to do integration by parts 3 times, because each time you do integration by parts, it knocks down that exponent by 1. So we went from x squared here to x to the first right here, and then the last time, our last integral was right here, and that time there was no x at all, it was just x to the 0, and that's why we were able to just integrate it and be done with integration by parts, just do that last integral sort of automatically. So that's usually what's going to happen, is that the x power just keeps getting knocked down by 1 with each successive application of parts, integration by parts. All right, so what happens if we replace the e to the x with sine of x? These are basically the two problems where you really want to be thinking to yourself, oh man, I bet that's integration by parts. E to the x and then sine or cosine, or something where if you keep taking its derivative, it never goes away. So we've got an x squared, which if you're thinking like I'm thinking, probably means we have to do integration by parts twice. And again, we're going to want to make our u the x squared term. The only time you don't make u the x squared or x cubed or whatever term is when the other function is natural log or something, but I'll get into that in the next video. But as long as you have a polynomial type thing times either an exponential or a trig function, you'll be wanting to make your u the x squared term, and then your dv will equal sine x dx. Alright, so our du equals 2x dx, and your v, just integral of that thing, is going to be negative cosine x. Alright, so plug and chug now once we got our u's and v's and stuff. So u is x squared times v, which is negative cosine x, minus the integral of v. So that's positive cosine x, because we had a negative on the cosine and also a negative in front, which canceled, du, which is 2x dx. Alright, so I'll just rewrite that, make that integral look a little nicer. So we can bring the 2 out front, 2 integral of cosine x, of x. I like to put the x in front. Alright, so now we're good to go. Once again, if I want to integrate x cosine x, can't do it right now without integration by parts, because if I wanted to use u sub, I just can't do it, because if I used u sub, it's cosine of u, so therefore my u would be x. Derivative of x is dx, not x dx. So I got this extra x I can't do anything about unless I use integration by parts. So once again, we're going to set u equal to the x term, which is just x this time, and our dv is going to be cosine x dx. So your du is dx, and your v, integrate the right side, and you just get sine x. Oops, no dx, because we just integrated that away. Alright, so at this point, we're ready to plug and chug once again. Just got to be really careful to keep all my previous terms. It's very easy to forget this thing. So let's go down here. Make sure we grab that right away so we don't forget it. Alright, then we got a plus 2 times, and now I'm going to do the integration by parts formula, because basically this right here is the integral I can't do without integration by parts. That's what's going to get replaced by all this uv dv stuff. So I'm replacing the integral x cosine x dx with uv. So u is x sine x minus the integral of v sine x du, which in this case is just dx. Alright, so finally I've got something I can integrate simply. The integral of sine is just negative cosine, right? So don't need integration by parts for that. And therefore I should be at my final step here. Negative x squared cosine x plus 2 times x sine x plus, because it's minus, but then we've got the integral of sine is negative cosine, so this ends up being a minus negative cosine, which is positive cosine x. And don't want to forget our plus c. Alright, so does that match the pattern we talked about? Again, we have a polynomial type term times something like an exponential or sine x or whatever, exponential or a trig function. So the first time we did integration by parts, this x squared, because this x squared was totally extraneous, right? We did not need it to integrate sine. That's what messes up our integration. So we did integration by parts once and came out with an x. So now we had an x to the first in an integral. Of course, x to the first is still extra, but at least it's not as bad as an x squared. We had to do integration by parts once again, this time with our u equal to x, as opposed to x squared from the first time. And then once again, the power of x got knocked down to the point where it's not even there anymore. This is where that would have been, except now you can sort of imagine there's sort of an x to the 0 right there. But point is that each time you do integration by parts and make your u equal to like x squared or whatever the polynomial term is, you go from x squared to x to the first to nothing. This had been an x cubed times sine x. Integration by parts 3 times. And to step down from x cubed to x squared, then x squared to x to the first, then x to the first to nothing. So whatever the power is on your x term, that's pretty much how many times you're going to have to do integration by parts. All right, so why is this one labeled trickery? I actually know why, but let's take a crack at it anyway, shall we? Find out what the trouble is. All right, so sometimes I can teach you more by doing it the wrong way than the right way, so check this out. Looks like we have an exponential times a power of x, just like we've had in the last couple problems. So let's just do the usual thing. Let's make our u equal to the x squared term, and our dv equal to the rest of it, so that's e to the x cubed dx. All right, so our du is equal to 2x dx, and to get v, we just integrate dv, so that's just v equals the integral of this stuff. What's the integral of e to the x cubed? Something's tingling in the back of my mind. If I integrate this, don't I have to match my u's and my du's and stuff? So it's not just e to the x cubed. I can't do that. I need my u is the exponent, so I need a u equals x cubed, which means my du equals 3x squared. But am I allowed to do du's inside of a dv problem? And oh my gosh. This is why this is a tricky one. But it's actually tricky, it's opposite tricky. If you try and do it with integration by parts, you're totally hosed, and you'll run off the skids like I just did. And no matter what I do, whether I just kind of like fudge my way through it or whatever, it's all going to be wrong. What I need to do is completely forget about integration by parts and just say to myself, whenever you sit down to a problem, you always want to try and integrate it with u sub first. So if we had just forgot about the fact we're in the integration by parts chapter and tried to do this on its own, we'd be like, well, I like integrating exponentials, so I'd like to use my e to the u formula, which means x cubed would be my u. So what would my du be? 3x squared dx? Oh, look at that. That x squared that made it look like it was an integration by parts problem is actually just part of my du. So if I just rewrite this thing, put that x squared off to the right where it belongs, it's really an e to the x cubed times x squared dx. And I've almost got perfect du matchup. I just need a 3 right here, which means I need a 1/3 out front. So it just becomes 1/3 integral of e to the u du. Pretty awesome, right? Now they're going to do this to you all the time in this chapter, and also all the following chapters, like trig sub, if your class is doing that, partial fractions, I mean, you name it. All these advanced integration techniques that show you how to do one particular type of problem, they're going to keep throwing curveballs at you by putting u sub problems in the mix too. And the reason teachers like doing that is because it actually makes less work for you if you're on top of your game. So they really like those because the students who really get what's going on and really know u sub really well will actually have to do less work in the test than students who don't recognize the u sub problems. So no matter what integration technique you're doing, integration by parts, anything crazier than that, always check u sub first because they're going to be in there. I've never seen a calculus teacher who doesn't throw u sub problems into the mix just to keep you honest so that you're not just plugging and chugging through integration by parts every time. They like it when you think a little bit. So anyway, so this became 1/3 integral of e to the u. So that's just 1/3 integral of e to the u is just e to the u plus c. Of course, now we stick back in for u and we get e to the x cubed plus c. So pretty quick and fast. Remember, the way we spotted this is at first I started down the road to integration my parts, but then my dv, just my u sub did not match up to the dv. And that's important. When you're taking the derivative of this stuff, you still have to use the chain rule. And when you integrate your dv to get to v, you've got to use u sub or whatever it takes to integrate it properly. So if you can't do the integral from dv to v, you just need to rethink it, reorganize stuff, whatever. All right, how about some trickery? This might be another one of those. So instead of just starting down the road, I'll show you what we should have done in the first place, which is to actually ask ourselves, hey, would u sub work for this? So if I wanted to do u sub, because this x squared down here is kind of weird, right? But if I wanted to do u sub, I want to use the e to the u formula, so my u would be the exponent of e, which is 1 over x. Which means my du is negative 1 over x squared. Oh, look at that, I've got an over x squared. So all I need is a negative here, a negative 1 there, match that, and then to compensate for that I got to put a negative out front. But now I've got it perfectly lined up for u sub. So there's just negative integral of e to the u du, which is just negative e to the u, which is negative e to 1 over x, not dx, plus c. It's supposed to be an e. Alright, so keep your eyes peeled for that situation. Alright, here's a fun one along those same lines. We're just going to want to be really clever. And this one, it turns out, we're not going to be able to use u sub, because as you can see, if you want to integrate this with u sub, the x cubed looks like it's extraneous, so we'll try and use u sub and make u our x squared. So integrate, cosine would integrate to sine, except that does not work, because if your u is x squared, your du would be 2x dx, not x cubed. So we need a lower power out here than we have out here. So we are in an integration by parts situation, but it's slightly different because we're not going to want to make u equal to x cubed. It's going to be an x power, but it's actually going to be x squared. And I'll show you why. If we make our dv, we figure, you know what? We always make the x junk our u, and then we make dv the rest of it, the thing that sort of derivatives wouldn't make it go away anyway. So dv is going to be cosine of x squared dx. But to integrate dv, I need to integrate this stuff on the right, this cosine x squared. But the integral of cosine x squared requires u sub. My u on that one's going to equal x squared, which means my du is going to be 2x dx. So I need a 2x right here in order to integrate cosine x squared. And normally I wouldn't be able to conjure one, except I can, because this x cubed is really x times x times x. You could rewrite this as x squared times x. So I'm just going to take this x and put it in with the dv. So that's where this x came from. Then of course, to get a 2 here, I got to put a 1/2 out front. But the point is that this x cubed, if I break it up to an x squared and an x, now things work out, so I can integrate cosine x squared. So I need a 2x right there, which means I need a 1/2 out front. So I get 1/2 sine of x squared. All right, so now I've got everything I need to plug and chug through the formula. Now remember, this u right here was just used for that u sub integration of dv. This is where it can get confusing, just like with chain rule. If you have nested u's, it can get confusing. But this u right here, I'm just going to cross it out because I don't want to get confused with the u's of the integration by parts. So when I plug and chug through this, I got u equals x squared times v, which is 1/2 sine squared. Oops, not sine squared, sine x squared. Minus the integral of v, which is 1/2, sine x squared, right? Yeah, times du. Oh, look at that, 2x dx. You might be tempted to cross out, cancel out this 2 and this 1/2, but actually, I just used that trick a second ago. My u is going to be x squared for this integral, because it's sine of u. So 2x, my du is just going to be 2x dx. So it actually worked out perfect to where this is just my du. So I can just do integration with u sub normally on this integral. So just copying down here, I want to keep this term as is. That's 1/2 x squared sine of x squared. I'm going to subtract 1/2 times the integral of sine x squared. Since all the du's match, the integral of that is just cosine. It's actually negative cosine, so positive cosine x squared. And of course we don't want to forget our plus c, as usual. Alright, so that was a tricky one. This x cubed ended up getting used for both dv and u, but that's just where practice comes in handy. You know, it depends on your teacher whether they'll ever get sort of this funky. Other teachers will get way more funky. I don't want to confuse things by showing you like a million different problems, most of which most classes never see. But the point is that just practice, practice, practice. If you have a really hard set of homework problems where there's a lot of trickery and a lot of having a real hard time finding u's and dv's that work out and stuff, just keep on practicing. Check out the examples in your book because they're probably similar to the ones your teacher will use on quizzes. And then worst case scenario, if you have a couple you can't do, ask your teacher. But talk about it with friends in class or whatever. Because u sub can be this integration by parts can be pretty weird as far as the complexity level varies a lot from class to class. I've seen this a lot in just calculus for business majors. So like basically your sort of simplest one semester calculus class in college tends to do integration by parts, even though it's kind of an advanced topic. But of course they also do it in all the hardest classes as well. So it really depends on your teacher and your curriculum as far as how hard the problems get. But I'll cover some of the harder types in the next couple of videos as well. Alright, so to summarize, whenever you have x to the n in front and then some function that's not a polynomial, you usually want to make your u the polynomial. And the reason for that is because in the process of doing the integration by parts, you'll end up taking the derivative of u. So if you made u equal to x squared, then the next time you do it, it'll be x, and it keeps knocking down one power at a time. If you made e to the x your u, you wouldn't benefit any from doing integration by parts because your u would be e to the x, and then your du would also be e to the x, maybe with a dx on it. But the point is, you wouldn't be any closer to solving this thing. And of course, if your u is e to the x, that would mean that your dv was x to the n, which means to get your v, you're going to have x to the n plus 1. So you'd be going backwards. You'd be making the problem harder on yourself than easier. Integration by parts, the whole point is to sort of knock down powers until you end up with an integral you can finally do after 1 or 2 or even 3 times going through the integration by parts machine. So your u is going to be something that would go away if you take the integral of it or take the derivative, such as x to the power. And in the next video, we're going to see that whenever you have a natural log, you actually also want to make that your u, because the derivative of natural log is just 1 over x, or 1 over u. So that's another way to get stuff to go away, is by making natural log your u. Same thing here, x to the n times sine x. Sine to the x, no matter how many times you take its derivative, it never goes away. It just keeps going sine, cosine, sine, cosine, sine, cosine. So you don't want to make that your u. You want to make that your dv. Then make your x to the n your u, so that way you keep knocking down from x to the n, x to the n minus 1, x to the n minus 2. Just keep knocking that power down each time you do integration by parts, because you want the x power to go away, or at least get knocked down far enough that it can be used for u substitution on whatever's left.